What's up, PreCalc? Here we are with 1.5. We're studying things from a graphical perspective today. So a lot of this is basically stuff you've had before, just in a different presentation, and it's kind of combining a lot of other things you've talked about in Algebra 2. Now it's just all together in one lesson, and it might take it just a half step further than you've had before. All right. So the graph is a collection of ordered pairs, x comma y, or x comma f of x. Again, this packet I'm using is available on Schoology, all right, and I believe Mrs. Johnson's completed packet is also up there as well. She's got way nicer handwriting than me, so you might want to look to see if that one's done if you want that. X comma y, or x comma f of x. X is how far away you are from the y-axis, left and right. Y is how far away you are from the x-axis, up and down. Okay, pretty common sense stuff there. Example 1, what is the domain of this graph? Find the function values for f of -1 and f of 2, and then let's talk about the range. All right, so we're over here. Domain, x's, left and right. We're going from -1 included, solid dot, up to +5, not included, open dot. Okay, so how can we write that? -1 less than or equal to x is less than 5. And if we're doing the interval notation, all right, we can go with bracket -1 comma 5 parenthesis. What are my function values at -1 and function values at 2? -1 comma 1, 2 comma -3. So -1 comma 1, 2 comma -3. So just basically reviewing, can you read a graph? And the range. Range is y values, up and down. So x is we go negative to positive. Range is we go negative to positive. What's the lowest we have? -3. Okay, and that was a solid dot, less than or equal to y, all the way up to +3. Okay, or if we went interval notation, all right. Vertical line test. Is it a function? Okay, so if you're looking at a graph and you're trying to decide if it's a function, we can use the vertical line test or the pencil test. Okay, if no vertical line intersects the graph at more than one point, then it is a function. So we're going through this. No one vertical line can hit this more than one time, so this is a function, yes. Same thing with this one. It's really steep right here, okay? So maybe you're thinking, oh, it's going to hit it more than once, but I mean, you could keep splitting that out infinitely. So this is still going to work, yes. All right, circle, definitely not, right? I can draw one line that's going to hit it, one vertical line that's going to hit it more than once. I know that's not a perfectly vertical line. Here, I'll try to do a better one. There we go, a little better. So that's a no-go. And here as well, no. If the graph of a function of x has an x-intercept of a comma 0, a is a 0 of the function, or root, okay? The zeros of a function of f of x are the x values for which f of x equals 0. We know that, okay? You know those from Algebra 2. All right, so kind of review finding those algebraically, or you could find them graphically. So we're going to find them algebraically here. All right, a little factoring action. Okay, to yourself here, there's a number in front that's not just 1x squared. We got 3x squared plus x minus 10. So we're going to have to factor this out. We're going to multiply front times back. What multiplies to -30 and adds to +1? How about a positive 6, negative 5? And then because we had a multiplier in the front, now we got to come back and divide these by 3. So this first one's going to be a 2. Sorry, you can't see that. First one's going to be a 2. So I got x plus 2. And then this one I can't reduce the fraction, so the bottom comes up in front, 3x minus 5. All right. Well, now what makes each one of these equal 0? Negative 2, positive 5 divided by 3. Okay, we can also get those graphically. 3x squared plus x minus 10. I'm going to make sure I'm in the standard zoom 6. There's our standard negative 10 to 10. All right, we can clearly see that one's going to be negative 2. We can test it out. Second trace, zeros. Slide over to where you think it is. It's about there, so left bound, left, 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 enter. Back down to where you think it is, right, 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 enter. Guess in the middle, ta-da, negative 2, 0. Same thing over here, second trace, 0. Slide over to where you think it is. All right, left bound, so left, 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 enter. Right, right, right. Guess in the middle. 1.6 repeating, or 5/3. Okay, so there it is graphically. All right, the rest of the way we're just going to do algebraically, and then you can do graphically on your own if you want. So where would this equal 0? All right, square both sides. 0 equals 10 minus x squared. Make it nice on yourself. Add the x squared over. So now it's positive. Square root both sides, and x is going to equal plus or minus 10. Square root of 10. Those would be our roots. All right, a fraction. Ooh. Okay, a fraction equals 0 when the top equals 0. All right, so step 1, we're going to make a little side note over here that t cannot equal negative 5, because that would make this whole thing undefined. So we are going to check out, when does the top equal 0? And we should be getting 3/2 or 1.5. All right, all stuff you've learned before. Okay, increasing and decreasing over an interval. Okay, the more you know about the graph of a function, the more you know about the function itself. All right, as you move left to right, so we're always talking left to right. You read a graph like you read a book, left to right, left to right, left to right. This graph falls from negative 2 to 0. It's decreasing. It's constant across here from 0 to 2. It's constant or flat. Okay, and then it's increasing or rising. It's increasing again from 2 to 4. Okay, so let's see if we can apply increasing and decreasing to these. All right, this one's tricky. It's increasing, and then here it looks like it's constant, but it's actually still very slowly increasing, and then it starts increasing faster again. So this is increasing everywhere. Or if you want to use interval notation, negative infinity, comma infinity. And remember, when you use infinities, it's parentheses because you really you can't ever get to infinity. So this one we got to think a little bit. It's increasing from negative infinity up to negative 1. And again, we're going to use the x values. Don't use the y values to describe this. We're using the x values to describe this because we're reading it left to right, and x's go left to right. So we're using the x values to describe where we're increasing and decreasing at. Then we're decreasing from negative 1 to 1. All right, and so we turned around. This one was increasing, and it kind of flattens out, and then it's increasing. Because we turned around, increasing to decreasing, there is going to be a spot where it's not doing anything, and that's going to be at exactly here, -1, 2, and that's why we used open parentheses or parentheses here and not brackets to include that point. Okay, and then we're going to be increasing again from 1 onward to infinity. All right, and you could also use inequalities for this. All right, increasing where x is less than -1, or x is greater than +1, and here we're decreasing between -1 to 1. Whatever you're more comfortable with. Okay, it all means the same to me. Whatever you're more comfortable with. All right, and here's a flat one. All right, why don't you go ahead and hit pause here and try this one on your own. All right, welcome back. Okay, tough to tell here because it doesn't have arrows. I guess we can assume that it's going to keep going on forever. I think that's what we did over here, I guess, too. So it's increasing from -infinity up to 0. All right. We're constant or flat here from 0 to 2. And then we are decreasing from 2 off to infinity. All right. There we go. Okay, and again, you could use inequalities like we did over here before if you're more comfortable with that. Okay. Max and mins, the points at which a function changes or where it turns around, are helpful to determine max and mins. That's what we got next. All right, relative max and relative min are just the individual high points and low points, and the overall maximum and the overall minimum would be the absolute, like, low point and high point. Okay, so these are relative because they're the turnaround points. Okay, and it's tough to say if this one's going to have an overall max and min because I don't know if this is going to go on forever each way. Okay. So basically the turnaround points are going to be your relative max and mins. Use a graphing utility to approximate the relative maximum of -4x squared minus 7x plus 3. All right, so we're going to type it into the calculator. Y equals, clear this one out, -4x squared minus 7x plus 3, graph. There it is. Okay, and we want the maximum. Second trace maximum is what we're looking for. Here's where I think it is, the top of the mountain. Left, 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 left. Back to the top of the mountain. Right bound, right, 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 right. Okay, what we're doing is we're squeezing it in between, and now the calculator is going to go through and find that highest point, -0.875. comma 6.0625. Okay. Average rate of change. The slope of a line can be interpreted as a rate of change for a nonlinear graph whose slopes are changing at each point. The average rate of change between any 2 points is the slope of the line through those 2 points. So it's still the slope, right? We're still doing a slope formula. It's just that it would be changing from depending on which 2 points you picked. If it was an actual line, the slope would stay the same. We're picking 2 points on a curve and doing the slope formula, and that would be the average rate of change between those 2 points. And that answer would change with every different set of points probably that we picked. Okay? It's still y2 minus y1 over x2 minus x1. All right, find the average rate of change from -2 to 0. So what do we have here at -2? At -2, it's -2 comma -2, and 0 is 0 comma 0. So we got y2 minus y1 over x2 minus x1. So we're going to get 2 both times. Positive 2 over positive 2, and our average rate of change would be 1. Okay, next one, from 0 to 1. Okay, we know our point at 0 is 0, 0, and at 1, we're at 1 comma -2. So -2 over minus 0, 1 minus 0. So we have -2 over 1. Our average rate of change is -2. Even and odd. We talked a little bit about this in Algebra 2. So you're just getting a bunch of stuff thrown at you here from Algebra 2. Okay. In the terminology of functions, a function is said to be even if its graph is symmetric with respect to the y-axis, and odd if its graph is symmetric with respect to the origin. The symmetry tests yield the following tests for even and odd functions. All right, f of -x, if that would equal the same thing as f of positive x, it's even. If f of -x equals the opposite or negative value of f of positive x, then we're odd. Okay? So we can test this out. Put in -x. G of -x would equal -x squared. Oh, I'm looking at the wrong one here. -x cubed minus -x. Okay, so that is going to be -x cubed. -x times -x is x positive x squared times -x again would be -x cubed. Minus a -x would be plus x. All right. So that would actually be the same as negative times the original function, -x, positive x. So that's going to be odd. X squared plus 1 is going to be even. X squareds are usually even. Unless there's any left or right shifting, then it's kind of tough to do that based on this definition, all right, of being able to be perfectly reflected over the y-axis. Excuse me. Okay. So -x squared plus 1. So -x times -x is positive x. So C is going to come out to be the same. So this one's even because it would equal the same. H of -x is equal to the same thing as h of positive x. So it's even. Mrs. Johnson has a special note written down here that most are going to be neither based on these definitions. Most are going to be neither based on these definitions. Being reflected, up here, being symmetric with respect to the x or the y, because then if you're shifted off left or right, then now you've wrecked your symmetry in respect to the y-axis or symmetry in respect to the origin. So most are going to be neither. All right, and we've got notes here that this one matches with that, and this one's going to match with this, similar to this. All right, this is a negative one, but this one's plus 1, so this would be, oh no, it is. I thought that was the x-axis. So this one does match with this graph, and you can see that it's symmetric with respect to the y-axis. All right, and this one matches our other one here, and you can see you can rotate, and then it would match with symmetry rotation. All right. All right, guys, that's all I have for you there on, what was that, 1.5? Okay, keep up the good work, guys. Keep working hard. We'll see you later.